this quantity del dot f, or del dot f as we define it up here, could be defined for a function of three variables. Obviously, if we had a rk, like a vector here, pi plus qj plus rk, it'd be very easy to do del dot that. We just add our partial with respect to z times k to the del operator and operate on this. We get px plus qy plus rz. Okay, and this is just a foreshadowing of how important this quantity is in hydrodynamics, electrostatics, and all kinds of fields. This is one of the big theorems when we extend this to three dimensions, and we're not going to actually prove the extension to three dimensions, but there's a three-dimensional analog of this. It has the same flavor. The integral of the divergence over this area here is equal to the flux of the function through the boundary. Okay, f dot dn. We're integrating the part of f that's perpendicular to the curve, the part of f that's pointing out of the curve, and that's equal to the integral of this divergence over the entire area enclosed by the curve. Now, you don't have a full appreciation at this point of what that means, or if you're viewing this later, maybe you do. It's a big deal. Okay. Now, there's this other operator called the curl operator. That's just the curl of f. We just use the del operator, but we do the del cross f, cross product of the del operator with f. And if we do that, and y'all are adept with the cross product, it's pretty clear that we get I times negative qz plus ry plus j times pz minus rx plus k times qx minus ry. And there's actually another theorem that we can prove from Green's theorem in 2 dimensions, and then that extends into 3 dimensions, that says that if we integrate the normal component of the curl to a surface, it's equal to the line integral of the function around the boundary. Okay, and that gets into circulation of a fluid. This is like divergence of a fluid. We'll talk much more about this. Those 2 ideas are the culminating ideas of the course. But in any case, here is how the curl is defined, and we go all kinds of places with it. The other thing I can say here, and I've got kind of a line of demarcation here, this separates what I've written here from everything else. And I just began to write this out because people didn't really have any problem proving this. If we do del dot curl f, then what are we going to get? Our x partial, our partial with respect to x operator is going to operate on the negative qz plus ry, giving us negative qxz plus rxy. Okay? Now, we have a qx over here that's going to be operated on by the partial with respect to z operator. And we're going to get a plus qxz, I guess. Okay? We're going to get a qxz here and a negative qzx here. Of course, the order of the partial derivatives doesn't matter, so that's going to cancel that. And then what we get from the ry here, operating on it with the x partial, we're going to operate on negative rx with the y partial here. These 2 are going to go away. And then, so are these 2. We then prove that the divergence of the curl is 0. Very easy to prove, very easy to write down. If you just follow the questions on the document, you're almost certain to get this if you do it carefully. More carefully than I often do. Okay, so that's a brief introduction to the divergence and the curl, and there are many things you can calculate to get more familiar with them, and of course I've assigned a lot of problems where you do exactly that. Okay, almost everything we do after we deal with a couple concepts of surface integrals is going to be with 2 main theorems, Stokes' theorem and the divergence theorem. Stokes' theorem relating the integral of the normal component of the curl over surface to the circulation around the boundary. That is the integral of the function around the boundary. The function dotted with the tangent vector. And to an integral of this type for the divergence. Okay. Get used to these things now so that doesn't hang you up later.